Hi, welcome to part 2 of the quiz review. This is going to focus on machines. Let's start with this idea of what is a machine exactly? Well, you should know that a machine is anything that magnifies the force, and that means either making it bigger or smaller, or that the device redirects the force, and often they will do both at the same time. So either one or the other, or both. Okay, conservation of energy applies to everything, and that means it applies to machines. And what that basically says is you won't get more out of a machine than what you put in. And so in this case that means energy. So basically the work that comes out of your machine, even in the best case possible, which technically doesn't exist, but if we could eliminate all friction, anything that robs energy, if we could eliminate all of it, the most that you would get out of your machine is what you put in. There's no freebies in nature, is what we believe, and it seems to be the case. Now in reality, because of friction and clanking and clinking and flexing, anything that's going to basically take the work you do and basically heat things up, you will actually get less work out of your machine than what you put in. So why do we have machines then? Well, because again, they can magnify force, and even though it may not get all your work out, a machine may result in a large enough force that you can do something that you couldn't do on your own. Okay, so the main thing that machines do is provide a mechanical advantage. So again, we kind of have this theoretical world where we eliminate friction or pretend it doesn't exist. And then we have the real world where friction and flexing and heating things do exist. For reasons that we talked about earlier in the unit, I won't go into the details, but TMA, the most convenient way often is to measure the distances. So theoretical mechanical advantage, basically what you do is you measure distances. You have to find the input side of a machine. You have to figure out what it is you have to do, through what distance do you exert your force, and then you go find the output side of the machine and you see, okay, what motion is there, what happens, and measure that distance through which the output force is would be exerted in theory. Okay, now actual AMA is, okay, we say the word actual about actual mechanical advantage is the actual force out that comes out of your machine divided by the actual force in. So this is where you have to get force sensors, spring scales, have some way of knowing what are the actual force in and actual force out. And the ratio of those is your actual mechanical advantage. Okay, so to determine the TMA, suppose we have a ramp. And this is what we did, and suppose this was 2 meters and this was 1 meter. Well, the theoretical mechanical advantage is the distance through which you must exert a force, and d out is the distance through which a force is exerted. Now, ramps are pretty abstract because we don't see anything being raised up like this, but that actually is what your ramp is doing, is raising something through a height, and that's happening while you are dragging the object up the ramp. So in this case, your dn is the length of the ramp, 2 meters. D out is the height of the ramp, which is 1 meter, and so you're going to have a theoretical mechanical advantage of 2. Notice no units because it's just a ratio of distances. So in any case, I mean, for all machines, basically, you want to figure out what the D out is. I always do this little D in and D out. So this is your D in. And I always have, like, my abstract machine is just lifting something up. And that's going to be your D out. Okay, but there are 3, actually I've already just talked about the ramp. So there are 2 other machines that can be a little bit tricky until you know how to analyze them. Then it becomes extremely easy. So let's look at those. Okay, one is anything that acts like a wheel and axle. Okay, with a wheel and axle, basically, typically you or something is going to be turning this large wheel. Whoa, that's bad, but you get the idea. Turning this large wheel around to make this guy over here turn. And so let's see if I have another. Okay, I'm going to basically get rid of hold on a second here. I'm going to get rid of that. That didn't work. Where's my eraser? I'm going to get rid of that and that and that and that. Okay, all right. So let's figure out how we get the mechanical advantage of this. Well, the theoretical mechanical advantage, as always, is going to be the distance you go through while you're doing your thing and divided by the distance that the output side of the machine goes through while you do your input thing. Okay, well, you're going to be, let's pretend that you're going to just turn this wheel. Now, you may not turn it the whole way, but let's assume that you did, and because you get the same answer whether you turned it just a tiny bit or the whole thing around. So it basically is the ratio of once around this big circle divided by once around this little circle. So that's going to be basically the circumference on the inside and the circumference on the outside. Well, what is the circumference on the inside? That is, what are these? It's what's basically 2 pi on the input side. Now, here is definitely, I'm going to write input because it doesn't mean on the inner one, the little one. It's the input one. And this is 2 pi r output. That's bad, I know, I just sneezed. I'll try to edit that out. Okay, so we see is the 2 pi's cancel. So it really is just the ratio of the input diameter to the ratio, I'm trying to draw half across, of the output diameter. But we basically can just say, well, okay, well, that's just could be the same as the input of the diameter, which is typically easier to measure. Is, okay, let's just take the outer diameter. Again, it's not output diameter, it's the big diameter, if that's what you're doing, divided by the little diameter here. Okay, so it's d big over d little. Okay, I thought I had a little. Okay, let's look at some examples. So they're all around us. So if you've ever turned the knob on a door, if you've ever opened a door, you basically get a mechanical advantage. This is D input. Right in there is D output. So I would guess that's about, maybe it could be around 3 to 1. On these guys, your input side would be this diameter, and the output would be, whatever the stem is that fits in there. So this, to me, just glancing, says, oh gosh, maybe 10 to 1, 8 to 1, 10 to 1, something like that. A steering wheel is the same thing. You turn a steering wheel, and there's a little shaft that goes down here. It's actually a pretty big shaft. And so that ratio of the outer diameter to the inner diameter is your mechanical advantage. Anytime you've turned a knob on a device, you used a machine. Here, you're going to basically typically turn this, and on the inside there's some little stem that goes into the machine, and that's what you're rotating. Okay, it continues. You've got a key can be thought of as a wheel and axle. You say, well, where's the wheel? You don't actually need the wheel. You're turning this. If you were to turn a key all the way around, you would be tracing out a circle. And there's your outer diameter, and who knows exactly. Let's just say it's kind of this is the inner diameter. So every key, if you've ever put a key into a lock and turned it, you've used a machine. So that's maybe 3 to 1. Okay, even a wrench. When you use a wrench, you're going to go trace out a large circle to make this inner circle. So it's just the ratio of the big diameter to the little diameter. Okay, let's just make sure, clean that up a little bit. Just so here we go. So suppose that you're given a knob or anything that basically where you turn a big circle to make a little circle turn. This would be so the theoretical mechanical advantage is the outer diameter or big diameter divided by the inner diameter. Not the input diameter, but the inner diameter. And here, I'm guessing I could fit, probably not exactly, but it's about 3. So I'm guessing that the big diameter is about 3 times the little diameter. So it's about 3 to 1, or simply a mechanical advantage of 3. Okay, the next general class of machine that we didn't go over too much is levers. And there is a very, very easy way to analyze levers. So what's a lever? Well, this guy is using a long, stiff, could be a board, could be a piece of steel, and so that is typically the lever is the thing that's going to be rotated. It's going to typically be balanced on something in the middle, somewhere in the middle, and that's called the fulcrum. And then you've got this, we're typically called the load, whatever he's trying to lift. Now he knows he's not going to lift this thing up in the air, but he's trying to get enough force out to basically roll this thing. But for our purposes, an output force is coming out here. He's putting some kind of input force in this general area. And what we'd see is that a bigger force comes out than what comes in. Okay, levers are also something that you see everywhere. Even if just a pair of scissors is basically a pair of levers sharing a common fulcrum. So when you put a force here, you get a bigger force out here. A crowbar is a lever. The fulcrum is actually whatever it pivots. Okay, so and levers will always pivot about something. There's the fulcrum. And so you put on the end of this thing, you put a force there, and you're hoping to get, and you will get, a big force out. A seesaw, it has a pivot point. That's the fulcrum. And who's to say who's the input output, but there is a down force here and an up force coming out here. Okay, you believe it or not, the tab on a soda is a machine. So here's your pivot point right there, and you're going to lift up here. That is your F in, and this part of the tab right here is going to push down with more force than what you put in. So every tab on a soda on a soda can is in fact a lever. So you use machines all the time. You don't even know it. Okay, let's talk about how we come up with the easy way of getting the theoretical mechanical advantage for levers. Okay, so what we have here is just a lever. We have the lever itself. We have our fulcrum. This is the load you're going to try to lift, and you're basically going to exert an input force somewhere on this side. I need to improve on my arrows. Okay, and actually what I need to do is learn how to use the thickness, and you're going to get a big force. I think that's a lot better there. Okay, now the way that you've learned to do it would be to measure this distance. That's D in, and then you would divide it by this, which is D out. Okay, but there is an absolutely easier way that we didn't get a chance to go over in class. Okay, if you look, you will see that there's two triangles. Here's triangle 1, and here is triangle 2. And you see that they share this angle, and I don't know all the geometry lingo here, but basically these are two similar triangles. And what that means is that the ratio, you have two similar triangles, that the ratio of D in 1 divided by D, I'll just call it D out, but that is on the second triangle. That ratio is going to be the same as, let me change color and get thicker. That's going to be the same as the ratio of this distance to this distance will be the same. And right now I'm going to call those, that's lever arm 1 divided by lever arm 2. Okay, because this is, in the lingo of levers, the distance between where you put your input force to the fulcrum is known as the lever arm. And the distance between, so you could think of this as lever arm in, so that's actually what I'm going to do. We'll say that's lever arm in, and the distance between the fulcrum, excuse me, and where your output force comes is lever arm out. Okay, so let me clean that up again. So normally, or what I told you before, is we can find the TMA for a lever by getting the distance through which your input force is exerted divided by the output distance. But with levers, a usually more convenient way is to measure the distance from where you put your input force to the pivot point. And we're going to call that lever arm in, and divided by, okay, and then the distance between the pivot point or fulcrum to the output force is the lever arm out. And we're going to abbreviate those like we always do. So lever arm in divided by lever arm out. Okay, let's put that into action. Okay, let's take a look at this guy. He is pushing down on the right side of this lever to lift up a 10 kilogram load. Now, right now I no longer really care about this 1 meter distance, except that provides a sort of a scale for us here. I'm going to guesstimate. Let me make that thicker. I'm going to guesstimate that this distance, I know it's probably not quite 2 meters, but I'm just going to say that it's 2 meters. This is our lever arm input. It's the distance from where he's applying his force to the fulcrum. And I'm going to say that the distance, I'm just kind of being very roundish here, but this distance is the lever arm out. And for our purpose, I'm just going to say that's 1 meter. It probably is actually a little bit less. Okay, so to get the theoretical mechanical advantage of this machine, we're going to take his lever arm, the input lever arm, divided by the output lever arm. And here we've measured this length as 2 meters. On the output side, we're just rounding it off to a nice convenient 1 meter here between the pivot point and where the output force comes out. You say, well, the output force, you could just pick the middle of the load. So, and that's where you want to use as your distance. So that's 1 meter. So we're going to say that this lever has a mechanical advantage of 2. Okay, let's do one more, and then we're going to wrap this up because it's going a little bit long here. Okay, so this guy, this is a little bit different. This would be like a wheelbarrow. If I were to draw the wheelbarrow like that, and this would be the wheel, and this would be the handle. So this would be a model for a wheelbarrow. Okay, so this is your load. This is where your output force is coming, and this is where you're lifting up on this wheelbarrow. Okay, what is the lever arm? Okay, sometimes your fulcrum is not in the middle between the input and output forces. So don't always think that's the case. But it is always, what it always is going to be is find where you put your input force. Find the fulcrum. And that is your lever arm in. Okay. What about lever arm out? It's the same idea. Find your output force. Measure the distance between that and the fulcrum. And that is going to be your lever arm out. Okay, so let's just put that into action here. We can say that our TMA is going to be lever arm in divided by, so this divided by that, and let's just use some approximation. This, I'm just going to say arbitrarily, is 2 meters. Again, this is, well, half the distance. So we don't even know. The lever arm in is twice the distance of the lever arm out. But I'm just making up numbers. Let's add that T there. Okay, so we're going to have 2 meters divided by 1 meter, or 2. So this has the same mechanical advantage as the earlier one. All right, let's finish this up by looking at the mechanical advantage of this soda can. Okay, so here is, the pivot point is actually not right in the center of this is just anchoring. The actual, if you look at a soda can, the actual rotation occurs right here. And pretty much everybody is going to put some kind of a fingernail right under there. So that is our lever arm in, and this is our lever arm out. So just making a rough approximation. This is not a straight on view, but I'm going to say, I'm guessing, is that the lever arm is about, lever arm in is about 4 times longer than the input one. So every time you open up a soda can, you use a lever that has a mechanical advantage of 4. Now it could be 3. We'd have to actually take the measurements here, but between 3 and 4 is that's a machine. That's pretty amazing. So you use machines all the time. Okay, we'll do efficiency in a little bit of in a third very short video.